Hello all, I'm Kevin Dragoe. I work with Chinook Consulting and geosteering is one of my areas of focus. We will look in this presentation at a very effective way of setting up large projects using Python script automation and then using Python for standardization of projects and data analytics. I will not go into too much detail with regards to coding. We'll just outline some coding directions that we found to be practical. We use well information sourced from Petroninja and imported large amounts of data into Starsteer as a means of initial project setup, and then with data analytics on projects containing dozens to thousands of wells. In practical terms, we will look at data extraction from well information aggregators, then repeatable routines to import object data from CSV files and placing it into Starsteer objects. We will look at the use of scripts to process data in meaningful ways, and also at some examples of data analytics deployed project-wide. Our data source of choice is Petroninja. We extracted data using the built-in interface that makes great use of well lists. We found the web interface to be fast and effective. Similar data exports can be produced from other data aggregators such as AccuMap or GeoScout. And we started by creating lists of wells, making good use of well select tools and sometimes filters if needed. We then use the data export feature linked to these lists. In Petroninja, data is exported in from thematic layers, one file per data type. Well headers, for example, are exported in one file, formation tops in another, casing, drilling events, surveys, each in a specific thematic CSV file. Production and completion data can also be extracted in the same fashion. Digital curve data, LS files, are a bit more tedious to extract. It has to be done well by well. We will look a little bit into that later. Now that we have these data files, we need to bring data into Starsteer using the built-in Python functionality. There are libraries for processing CSV files, but we chose to use basic Python code to parse these files. We built a few subroutines to extract exactly what we need and create Starsteer objects from that specific information. In quick succession, we split the CSV in lines, look for unique well ID or API in the line and use that as a reference, then determine column position based on how many commas we encountered in a header line before finding a keyword, the name of the parameter we're looking for. We then combine the line number with the column number to pair a parameter with a well entry and convert that parameter into a value for a Starsteer object. And these objects can be well names, coordinates, top names, and top name and MD value, survey depth, inclination, azimuth, and so on. We would loop through an entire file to generate wells based on header information, for example, or after the wells are created in a project, we would extract parameters for each specific well by looping through all lines in a file and finding matching APIs or unique well IDs. The subroutines to extract parameters by line numbers and columns are the same in these two scenarios. We normally start by creating wells and type wells. We look for parameters such as well name, unique well ID, API, X, Y, Z coordinates, operator name, basically filling the headers in a well object spreadsheet. Some of the parameters need to be strictly numbers, so strings for KB, surface, X and Y have to be converted from strings to floats, obviously. We would cycle through each line in the well information export and create a well and a type well for each line. With type wells, actually you will need to run the script once to create the type well object and then separately once more to populate the headers. If you try to create the type wells and populate headers in the same run, Starsteer cannot find the objects and returns an error. With surveys, we import measure depth, inclination, and azimuth into each well object spreadsheet. Some subroutines are applied by filtering for well name or unique well ID. There are generally 150 to 300 surveys in a horizontal well, so survey export tend to be massive. If we have to loop through a massive file for every well in the project, Python, which is a slow program to begin with, would take a very long time. We found it more effective to split the master survey file into separate files named by API or unique well ID and just parse the split files. This reduced the script running time from a few hours to a few minutes. Same routines are applied to extract the top names and the depths. Tops are then encoded into topset object spreadsheets, and separate top sets can be created for casing, completions, or other drilling events beside formation tops. When importing tops, it is good practice to run the script while Starsteer is in 3D view or correlation panel view. Otherwise, the top names will be displayed on the screen and clutter the screen in map view or geosteering cross-section. Starsteer has a particular way of handling tops, unlike other objects. I'm not sure what the difference is, but I noticed that when creating tops with Python script, for example, the window clipboard is taken over and cannot be used in other applications at the same time. Curve or LAS export in PetroNinja is not enabled for lists. However, there are dashboards and filters that can be used to high-grade wells for specific logs, and the LAS files can then be downloaded well by well. We used to deploy an external script to parse the LAS files and extract the unique well ID and rename the files based on that. But lately, PetroNinja did the exact same thing on the server side. So we can use the files as they are exported directly from PetroNinja. To import curves, we use the stock LAS import script from Starsteer library, modifying to loop through all the wells and then finding corresponding files in a specific folder, and also filter the logs using a list of mnemonics. Correlation and topicking. This part does not use a script, as the functionality in Starsteer is great and getting better. We use the correlation panel to format logs and tops, formatting one well and then using the apply to all option. And we used to deploy a script to generate polylines from top measure depths from a list of wells based on work done in the correlation panel. Now Starsteer, as of the last version, has a built-in mechanism to generate such polylines from the active formation top with values exported from all wells that contain that active top name. We generate points, XYZ, from formation tops, and we use this polyline to interpolate maps. We deploy Python scripts to go a step further in mapping, generating polylines from calculated formation thickness, if we have two of the same tops, and then map these trends. Now, rigorous QC need to be deployed in this project, as you will find rogue values that lead to bullseyes on maps. Before running any meaningful data analysis, we need to standardize the project. That involves everything from well names, API formats, curves and top names, and even some color formatting. We run scripts to read parameters such as tops, generate ordered list, and produce boilerplate dictionaries from these lists. We then modify these dictionaries and use them as keys to rename objects such as curves, tops, horizons, interpretations. For example, we want curves named ROP, not rate of penetration, ROP average penetration rate, and so on. Along the same line of thought, we want the reference horizon named lower Montney, not Montney B, target top, or top peak from seismic. Currently, we cannot actually rename curves with Python in Starsteer, So we do a workaround. We can create copies with new names and delete the old curves afterwards. Duplicate objects are problematic when running scripts, and we end up invoking ambiguous objects. A separate standardization run needs to be performed to deal with duplicates. Some are Python driven, some are manual, such as duplicate wells, as we cannot rename well objects with Python scripts. There is a wide variety of insight that can be learned from good data. Well spacing is a good one. There are example scripts in the standard Starsteer library to generate well spacing reports. They can be wrapped in for wells loops and calculated on large projects. The results can be displayed on maps like we have here in this example, identifying spatial trends. Calculated ratios are very easy to perform and can easily be generated project-wide using Python scripts. Curve averages can be generated, or values can be split into separate populations for analysis. Typical one, slide versus rotate, can easily be determined either from drilling parameters or just from ROP brackets. Curves or a combination of curves can be analyzed to determine reservoir quality, for example. Be aware of data step mismatch when analyzing multiple curves. We found it more effective to use Python to resample curves before we do analysis, so they can be compared more easily. Lithological parameters can also be calculated when curve behavior is known. For example, we know that ROP drops and gamma cleans up a little bit when encountering calcite stringers in the Clearwater formation. We can use this to determine exactly what proportion of a lateral leg was drilled through calcite stringers. This does not only lead to slower drilling, but also lowers production, so the insight has very practical purpose. Then cross-plotting well placement with other variables has obvious value, and using the geosteering interpretation generated in Starsteer is relatively easy using Python script. That would be this well placement parameter. This is an example of a project-wide recalculation. We can define thresholds or use statistical variation to calculate probable thresholds in curves with different calibrations, such as gamma. Then determine well lengths in and out of the defined values. The script can be run project-wide or on selected wells mentioned in lists, or in wells filtered by some criteria, such as by operator. Of course, project standardization has to occur before data analysis. Another element determined with script is a sidetrack point by comparing survey records in a multilateral well, as we can generally look for data from sidetrack point to TD. Projects in Starsteer generally have very good data quality because it was curated and QC'd while performing geosteering. Exporting surveys and curves from Starsteer is relatively easy to do with Python script, and the results are usually high quality data. A whole new batch of calculated parameters can also be exported using scripts from individual wells, well lists, or project-wide. This data can then be used to generate analytics and dashboards and can be updated periodically. Roji actually has a dedicated line of product doing exactly that with Solo Connect, which is built on top of data from Starsteer projects. Here are some examples of large projects built primarily with Python scripts. A Duvernay project encompassing the entire North Duvernay trend, generated from lists that filtered in only wells with Duvernay as a target formation. A second filtering pass was done to identify and bring in deeper type wells. We looked at drilling trends, well separation, and also used this project as a framework for geosteering Duvernay development wells for multiple clients. Another example, looking at the SAGD development in Christina Lake with tremendous well density. An additional pass was needed here to generate image logs from azimuthal resistivity curves. We used it again as a framework for geosteering new pads with regional mapping based on formation tops, used just as a guideline for the new pads. I should mention that it becomes impractical to open very large project in the Starsteer software. Thankfully, there is a solution. We use the Solo platform to store a large regional project and split it into more workable sub-project or virtual project, as they are named in Solo. There are many errors that occur while coding scripts, of course. Some are frustrating, some are funny, and this slide is just a blooper reel. This feedback dialog shows a script that ran for 3.5 days, and the long running time was due to one wrong indent that placed a large loop inside another large loop. This was a survey import script, and it went from running a few days to running a few hours, and eventually we optimized it to run in a few minutes. Some errors we didn't find an explanation for, but the results are clearly wrong, such as these well trajectories. When we encounter things like this, it's a clear sign of back to the drawing board. And now, as a conclusion, I will mention that deployment of script turned large project setup from a team working of 4 or 5 geoscientists working for 2 to 3 weeks to a job taking one person a few hours. When it comes to data analysis, escalation from well to pad to pool to region is relatively easy, and repeatability is key. Many of the results were achieved with Python scripts will most probably be replaced at some point by new software modules in the future, and I know Roji is working on a few angles on this. Thank you for your attention.